Now the third era of the Proterozoic eon, the Neoproterozoic, or late Proterozoic as it sometimes called. This is the time of many things, the rifting of Rodinia, and then another supercontinent towards the end, as we'll see. And also life starts to get more complex, gets kind of weird at the end, and then basically paves the way for the explosion of life in the last eon, the Phanerozoic, which will come after the Proterozoic. The picture here on the left, these are Neoproterozoic rocks in the Grand Canyon. That's the Chuar group, and this is on a hike from Carbon Canyon, a loop hike, around to Lava Canyon, and the beautiful sedimentary layers of the Galeras Formation there, striped. Those are sedimentary rocks of the Chuar group, which are, in this case, about 770 million years old. And then towards the end of the era, we see life forms like this. This is a member of the Ediacaran fauna from Australia, and these are all trace fossils. We don't have a single remaining body part of these animals, but they left their clues of their existence behind in the form of impressions, trace fossils. Well, the Neoproterozoic era spans the time from 1,000 million down to 541. Again, you notice that the 1,000 is a nice round number. That's easy to remember. It's because it's more or less an arbitrary boundary. 541, not so much. I mean, who came up with that? That is defined by either a radiometric date on a unit, like a volcanic ash or a lava flow, or it's defined by fossils. And so we're going to start getting these different time periods that have these kind of odd numbers because there are specific things that give us dates rather than just an arbitrary number. So 541 is the end of the Neoproterozoic and the end of the Proterozoic. Here's the time scale. We've gone through the Hadean and Archean, and now through the entire Proterozoic eons, 3 of the 4 eons of geologic time, and they all are included in what we call the Precambrian. So if somebody talks to you in terms of the Precambrian, it's basically everything older than 541. Okay, and so the Proterozoic was 2,500 down to 541, and then the Neoproterozoic is simply the last part of that. And there are a few different smaller units of the Neoproterozoic. These 3 periods, we will talk a little bit about a couple of them, the Cryogenian, cryo meaning cold, and the ice ages that are going to occur in this time, and then the Ediacaran period, as I mentioned, life forms that are going to appear in the rocks at that time. Okay, so the geography on Earth during this time, at the beginning of the Neoproterozoic, was dominated by the supercontinent Rodinia. And so where we left off, Laurentia was the core of it, and it's surrounded by a bunch of other different cratons, all assembled pretty much all together, forming a supercontinent that was probably the rival of Pangaea in terms of size. The green lines here are subduction zones. The supercontinent probably looked like this during the early part of the Neoproterozoic, around 1,000 million, when it was all totally assembled. 1,000 million down to 900 million. The letter Z is used to represent the Neoproterozoic. And so eventually, a little farther along, Rodinia started to break up, started to rift apart. And here's Laurentia. And where eastern Antarctica and Australia used to be right next door, they have now rifted away. And we think this began somewhere in the middle of the Neoproterozoic. And eventually, towards the late Proterozoic, these rifted away fragments came back together for the most part. Not all of them, but most of them, to give a little bit smaller supercontinent, and we call this Pannotia. So we actually have 2 supercontinents. So again, Z denotes Neoproterozoic, Y is Middle Proterozoic, and X is Early Proterozoic. And so if you're keeping score at home. And in fact, W is Archean, X is Early Proterozoic, Y is Middle Proterozoic, and Z is used to symbolize Neoproterozoic. Okay, so geographically speaking, in our part of the world, in western Laurentia, as I showed, East Antarctica and Australia are rifting away during the Neoproterozoic by the middle of it, and this is what it might have looked like towards the middle and end, where we have Laurentia here, the craton of Laurentia, the Wyoming craton and Superior and all that, forming the supercraton Laurentia. Arizona would have been part of that, Utah and all that. And everything west now used to be East Antarctica and Australia, and now you can see they've gone away, they've rifted away. During this time, the Neoproterozoic in Arizona, we were part of a rifted margin here of Laurentia, and the other continents, other cratons had moved off. The tectonics of the Neoproterozoic are really dominated by the rifting and breakup of rhodinium. And so this began at about 750, and the various parts started to scatter. Laurentia remained kind of tied to some of these cratons, but South China Craton and East Antarctica and Australia started to rift away. They wouldn't go far, though, but the rifting process was probably related by some kind of plume or superplume. And that's what this diagram shows. I mean, why do supercontinents break up in the first place? If you think about it, it's kind of an unstable situation. Heat's always trying to get out of the Earth, and you have these thick continental plates coming together, and the heat's trying to get out, and it's kind of got this lid on top. And so the heat is going to be knocking on that lid, trying to get through, and eventually it will start to do that, and it'll start to drive the rifting process. And eventually, you'll get a mantle plume, and it'll start to dome up, and you'll get fracturing and flood basalts and things like that. And as the rifting progresses, that's where you in the different cratonic areas separate. In between, you start making ocean basins. It's basically how oceans are formed. And so it's that kind of process that's inherent in every one of these rifting events. The analogy I always think of is a pond with lily pads on it, and they're all separate in various places. And as the energy in the system is less, there's less waves in the pond, they'll all come together and they'll all form a little supercontinent of lily pads. But as you add energy into that system, basically the heat trying to get out of the earth, and you throw a rock in the pond, you'll get ripples and they'll start to separate out again. And that's kind of what's happening with these cratonic blocks as they come together and stay together for a while, and then they'll separate, and then they'll come back together as tectonics brings them back together. So there's a cycle. That's why we see these supercontinents forming and then coming back together and forming again. So Rodinia is just another one of these in the process. And so the rifting apart of Rodinia, specifically Laurentia and East Antarctica and Australia, as they rift away from Laurentia, form an ocean basin. Consider like this, the ocean basin here. And that ocean basin is what's going to become the Pacific Ocean eventually. We call it Panthalassa. The ocean off to the west of Laurentia that was forming here we call Panthalassa. The Earth has always had oceans and could have had various names, but this is one that has a name because it's the ocean that's off to the west of Laurentia. Pannotia, another supercontinent, right at the end of the Neoproterozoic at about 600 down about 550, so pretty short-lived supercontinent. But it was a significant landmass, and we think it was more or less centered on the South Pole. So much of Rodinia didn't effectively rift apart totally. Some of the cratonic masses did, but they didn't go far, and shortly thereafter, Australia, East Antarctica, and others came back together to form this supercontinent, Pannotia. Okay, and so this is number 6 in the cycle, right? And we think it was centered on the South Pole, and for various reasons, this might have helped trigger some global ice ages at the time. And that's what this cool picture of Pannotia at about 600 million, that's what Earth might have looked like. Pretty cool. The southern part of the planet, mostly continental, and the northern part, mostly ocean. This was destined, though, to rift apart, and when it did, Laurentia was the one that rifted away, and there was an ocean formed in between Laurentia and what was remaining of Kenosha, and we call this Iapetus, as we'll talk about later. But this remnant of Kenosha that Laurentia rifted away from has a name, and it's called Gondwana. Some people call it Gondwana land, but Gondwana, it's almost a supercontinent in its own right, but this is still centered on the South Pole. It's a massive, a bunch of supercratons, and eventually Gondwana is becoming a major piece of the last supercontinent, Pangaea. Neoproterozoic rocks of western Laurentia include the younger part of the Grand Canyon supergroup. There are a couple different units to talk about. The oldest one of these is called the Nankoweap Formation, and it has an age that's something less than 800, but down to about 770. Again, there's reasons why we give this age range. We don't have a whole lot of fossils in these rocks that help dating. It's mostly on volcanic ashes and what are called detrital zircons and stuff like that. But these are sediments, sandstones, and mudstones that were deposited in mud flats near the ocean. That's the Nankoweap Formation. This is a picture from the eastern Grand Canyon, and all the rocks on top here are Paleozoic rocks, the Redwall limestone, and the lowest one here is the Tapeats sandstone. But these reddish layers right here, that's the Nankoweap Formation. The ones at the bottom, the darker colored layers, that's the Unkar group. Y for Middle Proterozoic, U for Unkar, and C for Cardanus. These are the Cardanus lavas. And ZN is Neoproterozoic Nankoweap. And so these are the reddish mudstones and sandstones of the Nankoweap Formation. In the strat column here, here's the Nankoweap. The Chuar group is the younger of the two groups in the Grand Canyon supergroup, and its age is 770 down to 742. Again, shallow marine mudstones, siltstones, and even some carbonate rocks. And so this again is a view right here of the Chuar exposed in the eastern Grand Canyon. Beautiful sequence of layers there. The Chuar group itself has a couple formations, the Galeras and the Quagunt formations. And in these sedimentary rocks are actually stromatolitic fossils like this one. It's like a little golf ball, cut cross section of a golf ball, or a little cabbage or something like that. Here are mud cracks exposed in a bedding plane. So everything you see here, we call the Galeras formation. And like this stromatolite here is coming from right over here on the right. Well, like the Nankoweap Formation, which technically isn't part of the Chuar group, even though it should be, the 60-mile formation is similar. And it has an age that is around 742. It's probably a little bit younger. And these are continental red beds. So they're basically mudstones and breccias that are reddish in color because of the hematite content in them. And it's thought these are related to extensional faulting. These were debris flows coming off of fault scarps. And the reason the faults are there is tensional stress and rifting apart, and this is the rifting of Rodinia. So it's thought that these rocks represent the initial breakup of the supercontinent Rodinia. So this is the youngest Proterozoic rock we have in the Grand Canyon. It's only preserved because it's in these downdrop basins. It's eroded everywhere else, but it was preserved because of this extensional faulting dropped it down and kind of preserved it. And so we don't see any Proterozoic rocks in Arizona that are younger than this. The climate for the end of the Proterozoic, this is kind of a big topic because it has major relevance for life on the planet. And so there's an ice age or series of ice ages that occurred in the Neoproterozoic, and we call them the cryogenian ice ages. Some people just call it snowball Earth. This is the time between about 710 and 640, and here's the time scale, and these are the periods of the Neoproterozoic era. The cryogenian had the two biggest of these ice ages, where we think the ice covered the entire planet. maybe not every square centimeter, but at least in its extent from equator to North Pole, ice was found in two of these ice ages. So widespread glacial deposits around the world suggest there were these two ice ages that lasted millions of years. This idea was brought forth by a number of scientists, including Paul Hoffman and Dan Schrag, shown here. And what they're standing in front of is a big glacial dropstone. Okay, and they're in Namibia. It's like, well, how can a glacier be in Namibia? And a lot of people said those dropstones formed at the poles, and plate tectonics brought the rocks to where they are today. And that's a good idea, but you can actually do paleomagnetic studies on these rocks and see where they actually originally formed. And these dropstones were formed near the equator. And so how do you get glacial dropstones near the equator if you don't have ice there? And so that led people to believe, well, if you have ice at the equator, the entire planet was probably covered, or most of it. So from work that's been done in the 90s and then afters, but people have been kind of piecing this together for a while. We think that the end of the Proterozoic had at least two major snowball Earth events. Of course, this could have happened even earlier in the Huronian glaciations, ice ages previously. What brings this on? Again, you have a mass of continents centered on one of the two poles. That helps. But there are other triggering factors that could have been responsible as well. The bottom line is we think that Earth probably completely froze over, or at least most of it. Okay, and so the real dilemma here is, well, if it did, then how did it unfreeze? And so, again, that's one of the articles we'll have in class that deals with just this whole idea. It's a major theory, and there are a lot of different people that have worked on it, and it's a pretty cool idea that relates the geology to the kickstarting of advanced life that happened after this. And what ice age slide would be complete without frozen or frozone? Well, I mentioned the Earth freezing over. The dilemma is, well, why are we here? How could we be here if the Earth froze over? How did it unfreeze? Well, one of the bits of evidence was the fact that there was an ice age, and that's the glacial deposits. And so in this outcrop here, that's at the lower part of the outcrop, these glacial deposits, but they're directly overlain by what are called cap carbonates. And the thick sequence of sedimentary carbonate rocks represent deposition in kind of warm equatorial water like the Bahamas. So it's like two radically different things. How do you get one right after the other? No unconformity, no break in time in between. It's thought that you had this ice age occur, and it got so cold that there wasn't a whole lot of water vapor in the atmosphere. It would have been just like the North Pole say, it's, commonly blue skies and all that. It's just too cold for liquid water to be present in any major quantities. And so volcanoes keep erupting, and volcanoes are emitting a lot of water vapor, but also other gases, greenhouse gases, carbon dioxide, and others coming out. So a huge amount of carbon dioxide is being added to the atmosphere. Typically what happens is that carbon dioxide gets in the atmosphere, and then precipitation scrubs that carbon dioxide out. Okay, water vapor combines with the CO2 to form carbonic acid, and then it falls on the earth, and there you go. Rainwater is slightly acidic because of that. But there was no precipitation because it was so cold, and so the carbon dioxide abundance is built up to extreme levels, thousands of ppm. Today it's about 400 ppm. These levels were in the thousands. And so the progressive addition of all these greenhouse gases to the atmosphere at some point crossed a threshold where there was enough greenhouse gas to trap the heat from solar radiation, and it caused a very intense sudden warm up, and that's pretty much what melted the ice. And then when the rain started, it's falling through this supercharged CO2 atmosphere. The rainwater would have been very acidic. It's hitting the ground. It's dissolving rocks. All sorts of things are happening. But that's more or less how what brought us out of the ice house was the addition of these volcanic gases, eventually forming a super greenhouse effect. The whole problem biologists have with this is, well, how would life survive the millions of years when Earth was covered by ice? And there's been a lot of research on this since, and a lot of life forms at the time didn't care. They were on the seafloor. They weren't photosynthetic. They're chemosynthetic. They had no problem with an ice-covered Earth. But even photosynthetic organisms can live in certain conditions under the ice. We see that today. And it just depends on how thick the ice is and how transparent it is. So the slower ice freezes, the less impurities it'll have and the more clear it'll be. So life can survive, and certainly it can survive in local areas around hydrothermal vents. Neoproterozoic life wouldn't be complete without talking about our old friends, the stromatolites. They're still very abundant during the Neoproterozoic, and afterwards they're going to start to tail off because they're going to be replaced by a whole suite of other life forms, not the least of which is green algae, which is photosynthetic algae, eukaryotic, and this appeared about 1,000 million, and we think these are more or less the ancestors to land plants. So we don't have land plants yet, but it's the first sign of them. So green algae. Animals will start to come in at the very end, multicellular eukaryotic organisms that we can consider animals that have bilateral symmetry and all that. And so there are microfossils and rocks that pushing the first animals into the Neoproterozoic. And the first sponges and corals are appearing at the very end, about 600 down to about 580. Again, when you look at this picture here, notice the scale. That's why scale is important. That's 200 micrometers or micrometers. So that's pretty small. That's not like table size or hand size. That's a microscopic sponge from at the very end, as I mentioned before, we started getting some weirdness in the form of the Ediacaran fauna, sometimes called the Ediacaran biota. And these are a whole suite or assemblage of trace fossils made by some kinds of soft-bodied organisms. There's different types, and it's, as always, more complicated than we talk about, but there's different types of these that more or less span the range between 575 down to the very end about 542. So there's all sorts of different types. Again, they're all impressions or trace fossils, whether it's Spergina or Kimberella or Dickinsonia. This is a reconstruction diorama of the seafloor showing these different organisms. They're macroscopic, meaning that you can see them without a microscope. And that's inches. The Dickinsonia there is about 3 or 4 inches in size. They're bilateral in symmetry. Notice you can divide it right down the middle there into 2 parts. Okay, and so that is very distinctive of an animal. These are the earliest real macroscopic large bilateral organisms, sometimes called bilaterians. And so why now? And it's thought when you look at the timeline here, here's the Cryogenian period of the Neoproterozoic, and then the Ediacaran is the final period of the Neoproterozoic, sometimes called the Vendian. But anyway, those major ice ages that happened just previously might have been the dynamic evolutionary impetus to spur on some of these changes. And so we're going from simple red algae to life forms like this. Okay, and so there are a couple other aspects that could have happened. There were a few other little glaciations that occurred. There might have been an impact in there. It's kind of hard to say exactly what is driving the complexity, the push towards more complex organisms. But for whatever reason, these creatures did evolve, and then suddenly they go extinct. And right at the end of the Neoproterozoic, we see an end of these, but then we see an explosion of diversity of other animal forms. And so the Ediacaran fauna are somewhat of a mystery. They appeared, and they were very strange and new life form that Earth had never seen before. And then they were gone almost as soon as they appeared on the scene. But they were replaced by lots of the ancestors of animals that we know of today. And that was called the Cambrian explosion of life, what followed this Ediacaran fauna. So it's interesting that these glaciations could have been the reason for this evolution of animal life, which is why we're here. Without the glaciations, would we be here? So glaciation is a evolutionary factor. Interesting.